So good morning, dear colleagues. Thank you for joining InnoDay's 22 webinar, Charging, Storage, and OPS System for Ships and Ports. InnoDay's events are a sequence of seminars organized by Motors Foundation, dedicated to innovation in the sectors of alternative fuels and energy, maritime transport and ports, digitalization, and other environmental matters. I'm Emil Warowski, Managing Director of Motors Foundation, and I'll lead you through the sessions today. I would like to share a few slides now. Okay, so today's webinar, we concentrate on electrification, charging, battery storage, as well as OPS system for ships and ports. The first session will include different charging solutions in battery storage for hybrid and full electric vessels. During the second session, the webinar will focus on OPS systems and infrastructure, as well as EU financing opportunities for shoreside supply and battery charging systems. As a conclusion, we will get more insights on the OPS infrastructure deployment from a couple of leading BSR ports. Today's webinar's partner is the Baltic Ports Organization, and presentation will be given by Mr. Bogdan Hogdarkowski, Secretary General, during the OPS session. Also, within the first session, we experienced presentation dedicated to Hyperbot project, a Horizon program project, which is planned to start in June 2022. We will also have presentations from Rainer Altmappen, Aboutschlemann Technique, a Wapte company, Iman Morigi from Brink, Thomas Gerrit from Helix, and Peter Rampen from Damen. After a short break, we will continue with a second session dedicated to onshore power supply infrastructure. We will see presentations from Monika Rozmarinowska-Mrozek from Akcja Forum, Andreas Slotze from Port of Helsinki, and Nikolai Haubroer from Port of Copenhagen, Malmö. So highlighting again our partner at InnoDay's 22, it's the Baltic Ports Organizations, also a Hyperbot project partners, and the event's media partners, Gospodarka Morska, Baltic Transport Journal, and Wysokie Napięcie. And last words before we start to the webinar participants. Please ask questions to the speakers and share comments by using the chat section on our YouTube channel. So without further delay, I would like to start and invite our first presenter, Mr. Rainer Altmappen from Aboutschlemann Technique, to give us a presentation on charging solutions and applicability for different vessels. Rainer, you may start your presentation now.
All right. Well, first of all, thank you very much, Emil, for number one, organizing, and number two, for having us. I think it's really a very important time in the electrification of ferries and ships, because we now have the political support that enables us to come with solutions for charging different vessels. And I want to elaborate a little bit today on the different and the complexity, what it means to charge ships of different size and different power needs. And first of all, I want to introduce myself. I'm the Director for Ports and Maritime segment at Aboutschlemann Technique in Schüttorf. Aboutschlemann Technique, we are an entity, we are part of the American Wapte company. We are an organization that takes care of providing energy and data to movable consumers in the widest sense. And organization, which is founded in 1912, is located in Northwest Germany. And from there, we mainly make pantographs for the railway and bus industry, but also for mining, and obviously for all sizes of railway systems. We are 650 people approximately in Schüttorf and 110 in our Polish subsidiary. A few are located in Berlin, so we feel we are close to the client, but we are for sure able to charge high security systems in public transportation. Having said that, I want to introduce you to what our journey was in the past 8 years when it comes to electrification of vessels. But first of all, I want to give you a rationale for the motivation why we went into that. And it's all based on the Paris goals, which were defined back in 21, and before that, actually, European directives for reducing the impact of CO2 go all the way back to 2014. And there is a goal to reduce the emissions in shipping CO2 down to 0 by 2050. There is a milestone targeted for 2030 where the emissions should be reduced by 40% compared to what the emissions were in 1990. And for the marine industry, the IMO, the International Marine Organization or Maritime Organization, has taken over the lead to orchestrate all the efforts of the marine family worldwide. It's more than a nationwide, it's a fully international orchestra, so to speak, with very different speeds and intentions. And we want to focus today on mainly the technical requirements before my fellow presenters are going to go into the other topics. So the technical world will enable this CO2 reduction. And the shipping industry or the marine industry has many different levers to actually facilitate that. I've written down a few for you. Fuel is certainly one of the factors which can make a difference if we are going to look into ammonia, biofuel. Hydrogen is a big topic also to power fuel cells. Engine technology may change. We have a first step towards battery operation here when we use peak shaving batteries, i.e. for discrete positioning or others, or tier 4 diesel engines which are offered, which in fact reduce the CO2 emission, but they can only be the first step. It must be the goal to reduce them down to 0. The vessel designers, the naval architects have done a great job to get more out of the hull and the propeller and drive system, where electrical drives are, especially when it comes to ferries and cruise liners, already very well known to the marine family. So scrubbers, engine control systems, etc. All those are topics which are possible. But today I want to elaborate on the battery electric ferries and on shore power, which means land power supply to ships when at berth. To differentiate between these two topics, a shore power system provides energy to the ship when the ship is at berth. Take a cruise liner, take a container vessel. They can switch off the iron of the motor when they are sitting there for a day or two. And that's why this one thing is referred to, or this process is referred to as cold ironing. Here we have standards already. We have a pretty good interchangeability. That means that different ships already can call on the ports, because the power supply systems, which are basically cable reels which connect the landside box, and I'll show you a few in a second, with the ship, are flexible enough, volatile enough to provide power to different ship sizes, no matter where their contact point on the vessel is, and no matter what the geometrical requirements on terminal and ship are. When it comes to ferry charging, there we have a slightly different concept, namely automatic connection, because the amount of calls in a terminal per day can be as high as 40 or more, and therefore connecting to the grid to charge the onboard drive batteries is something that is recommendably automatical. Now, this requirement to go automatical has prevented the industry so far from standardizing it. We can be happy that when we can realize interchangeability in a fleet, but fully automated contacting is subject to highly individual solutions. One word more why one would go for electricity and also for plug-in electricity, because when we drive a hybrid vessel, it's pretty much like in a car. I can charge a battery from through the diesel engine, but the diesel engine, even if it is Tier 4, will not help to reach the IMO goals. I have borrowed this chart from one of our customers, and they use their current vessels with diesel engines, and if they use diesel hybrid vessels to optimize the diesel operation around the sweet spot, they found that they will not meet the emission targets because they can only reduce up to 16% of CO2 emissions. When that scenario is shown here in this timeline, so in the bright green timeline, we will see a reduction of probably 16% until 2040. That is the horizon that they are looking at, because their target is to reach 30% of emission reduction down to 30% by 2040. Now, they went through different options and found that only the plug-in hybrid solution, whereby the onboard batteries are charged from land through a shore connect or through a ferry charging system, can help to reduce the IMO targets. So they will be down by 76% by 2040, which is represented here in this dark green chart. So I think that the rationale behind it, as we see it today, and with the technologies that we have at service, are clear, namely that that electricity and charging from land seems to be the major or the key way to reach the goals. To give you some insight into the complexity, I want to introduce you to the shore power supply systems, which are the standardized systems as we have them today for charging container vessels, for instance. Here you can see that cable reels are lowering down cables from the ship to connect them to landside connection boxes. So it is as if you have your own extension cord and plug into a landside supply. Here we can charge up to 6.6 kilovolts. It's all standardized as per IEC, ISO, and IEEE requirements. It's the same plug and frequency between 50 and 60 hertz, no problems. If we have the same ship, which is calling on the port all the time, then we can go for stationary systems. And the reason why cranes like these are used, that is because the weight of the cable to provide 1,700 amps is just so big and so heavy. A cable like this would easily weigh 7 to 8 kilograms per meter. And if you need a whole bundle, like 4 or 5 of them, as you can see it here, plus plugs which are in the neighborhood of 50 kilograms, then health and safety requirements request you to support that transportation. To reach a cable over to the ship, a crane is needed, and to roll out the cable from the connection box to where the ship is, a cable reel is needed. So the combination of both are married and combined on the back of vehicles, which are volatile enough to go from one plug to the ship and back to the next job. We have also seen different solutions where clients wanted a tidy terminal where we have buried the cables because it was requested by health and safety requirements. Now on solutions like these, where you have an ergonomic connection box, here you can see the big cables and so on. You will be able to invite every bigger ship with land power supply requirement at your berth, because the unit is flexible enough to provide the requested power. When it comes to ferry charging, the whole thing is slightly different. The need to charge a ferry automatically requests us to really look deeply into the daily operations, into the need for power that is required. Is it high voltage, low voltage? Can we get enough energy from land, yes or no? If not, the integrator companies like Helix, for instance, need to think about using landside battery banks. All that is being considered, but it's all about availability and providing a crew the easiness of charging the ferry sufficiently. Now, there are different solutions, but so far the amount of different solutions is rather high, because some have the requirement to compensate tide, others need to be charged from the top, from the side, from the front, and therefore we go through a whole bundle of questions to find the very best solution. And the only people who can answer that at present are the operators themselves. To give you some examples of what has been done so far, pantographs, which have been used for ages in electrifying buses, are now being transferred to swimming buses, to water buses. When you mount them on a floating pontoon, you can overcome the tidal problem as a ponton and the ship are traveling in the same direction. This draft here was provided by Damen Shipyards, and the concept as such has been taken or brought into reality, for instance, here in Norway, where a floating pontoon is used to charge 2 ships at a time with a double pantograph. So here the power requirement was a total of 3 megawatt of power, and I hope I can start the video.
Since the dawn of recorded history, ports and maritime activities have been key to the development of commerce, prosperity, and sustainability. Aboutschlemann Technique has been serving this industry with superior products and technology for decades. Whether by providing onshore power
here in this nicely shaped support tower, are compensating the ship's movement, and that is something that is of particular interest when we talk about ferries, because especially when you have a Ropax ferry and trucks and cars are leaving, the ferries tend to roll over a tiny little bit.
Since the dawn of recorded history, ports and maritime activities have been key, and cruise liners as an alternative to onboard diesel generators. And this critical IEC 80005 as rapidly and securely as possible, and with the least amount of manpower.
So we are a ferry that is charged from the top. Ferry charging from the side is more or less a classical approach, providing you have a terminal that enables the access to the ship from the side. If you can do that, then the center of gravity of the vessel, where relative movements are minimum, is technically, or from an engineering standpoint, probably the most convenient one to allow safe connection and very short connection times. Because the shorter the connection time, the longer the net charging time, the more flexible the ferry operator is in his schedule, because he doesn't have to wait until the batteries are charged when you can charge up to 8 megawatts of power AC into the onboard batteries. Having said that, we have seen that the need to power ships increases, and therefore also the impact on the local grid increases a lot. So the chargers develop into two different new directions. Number one, higher charging capability. We will be able to provide, or the industry will be able to provide chargers 10 megawatt and beyond in about a year or two from now, because there is the need as the ferries go bigger and longer distances. The other development direction is interchangeability. And that means that different ships with different width of berth can call on the same terminal. And therefore, more flexible ferry chargers are needed, which were requested and realized, for instance, by Damen shipyards for a project in Canada for the Ministry of Transport Ontario, and where the chargers actually fulfill this requirement, namely to charge a ferry which is I think 60 meter and one which is 80 meters long and have different berth. Connection times again here were key, but also the need to compensate the tidal movement and the rolling of the ferry. So the requirements have been considered, and we will see that in reality later this year, as I heard from Damen. Now, as I said, the need to standardize is also the topic of today's conference. The standardization of the marine charging systems are now being bundled in the Hyperbot project. I don't want to elaborate too much on that, but at the end of the day, the challenge is to provide onshore power to ships of different size and of different power requirement. We will see that in the multi-megawatt charging or power transfer range. And we have 19 interdisciplinary partners from 9 countries, which are working on a solution that incorporates also the grid and the vessel, but also the market impact of that. And the whole goal of the project is to provide a technology readiness level of 7, meaning that we will have a functioning model. We see a vessel here that is one of the potential prototypes, which shall be used as a demonstrator in Norddeich on the German North Sea coast in about 2-3 years from now. And I'm curious to learn more about that myself in today's meeting. We are learning that the complexity that we have in the past has given us a lot of experience as users of this technology to hopefully standardize it. The outcome, however, will be, and those are my conclusions, that as we have standardized the shore connect, we need to standardize the automatic connection and the electrification of ferries. Otherwise, we will not be able to meet the ecological challenges that we are facing, Paris goals in brackets. The governmental and the European funding support is there, as we see it in other regions of the world, in NAFTA, in Australia, which are already suffering from the outcomes of global warming. The port's individual requirements must be considered, because we will not be able to harmonize all the port arrangements. So the challenge will be on the side of the charger. We will go on to find customized solutions, but also for tailor-made business solutions, as the electrification of ships have shown in the past that there is a business case, as you can reduce crew headcount. And therefore, we think that the need to reach the IMO goals, plus the commercial viability of going electric in professional shipping, is there, and the days were never better than today to facilitate that. Therewith, I want to conclude. I'm open for questions, and I thank you again for having the great opportunity to be on this panel here today. Thank you very much.
Rainer, thank you for the informative presentation. Excellent in representing different charging solutions for ships, and on the pole side as well. I would like to inform you that your video was fully visible on YouTube channel for our participants. So everything was delivered to them. We don't have questions for now, but I would like to ask you to remain with us if you can for any further.
Yeah, that's with great pleasure, and I'm keeping an eye on the chat window. Let's look forward to the next presenter.
Sure, thank you very much, Rainer. And now I would like to move to the next presentations, which is going to give us some more light on the ship side, where we've got this battery, different designs of the batteries and optimization of these batteries. With that said, I would like to invite Emmanuel Ricci from Brink to give us a presentation on ship's battery design and optimization. Emmanuel, you may start your presentation now.
Yes, thank you, Emil, for the introduction. So I just turn on my camera and then I will share my screen.
Thank you.
Okay, so I hope that you see my screen. First of all, my name is Iman Wargi. I am a research director at Brink. The Brink is a non-profit organization. We are working on green technologies around the ship side, but also in mobility sector, stationary sector, and also some activities around the hydrogen as well and renewable energy. So today my session would be about battery design and optimization with a focus on the marine sector. So as you can see, the European Green Deal set some targets to reach the net zero emission of greenhouse gas by 2050. And in order to reach this goal, the European community must evaluate different resources of energy into a sustainable and circular economy. For the road transport, rail, or e-mobility sector, already some significant steps has been taken, and now is with the decreasing cost of batteries, we need to go to the marine sector. And to adapt that to this waterborne sector. So to do so, we need to answer some challenges in terms of the design. That's why my first topic would be about the battery system design, prototyping, and manufacturing. Then, of course, there are some challenges which are related to the integration or safe integration of battery into the ship. And that's why it brings me to the second topic, which is about the thermal management system solutions. And of course, another topic would be about the smart control and how to transfer the physical orientation of the whole system to the control orientation. And that's why it will bring me to the two last topics, which are about the advanced multi-scale and multi-physics models, and also the smart BMS and cloud solutions. So first of all, here in my slide, you can see a different modeling approach in order to design a battery system and optimize the battery system. Here in the left side, you can see electrochemical modeling, mechanical modeling, a lifetime modeling, where we estimate the end of life in two different modes. And here we have the calendar mode, where the end of life is estimated in the storage, and also the cycle life mode, where it's the end of lifetime is predicted, where the storage is in application. Then we go also through the electrical model, thermal model, and electrothermal model. All those models, they have different levels of modeling, starting from material level, going to the cell level, to the module, pack, and also the system level. So following those approaches will provide at the end a complete model of the battery, combining electrical, thermal, and mechanical models. And the idea now is to find a modular approach which can fit to different vessel application, different operation. And that's why it brings me to different also modeling approach to transfer the physical orientation into control orientation. So we start here by the mathematical approach, where the focus would be about equation-based approach to simulate the physical and electrochemical process occurring inside the battery. Then a fractional order model, which is derived based on the principle of electrochemical impedance spectroscopy. Then the ECM model, which is using parameters such as the OCV, cell temperature, and so on. And then the empirical model, which is based on electrochemical impedance spectroscopy tests. However, those empirical models, they have some domain-specific strengths that limit utility outside the envisaged application. Then we go through the physical-based model and to end by the data-driven model, and here where a black box is used and some machine learning algorithms can be used in order to transfer this physical orientation to control orientation. So by following all those approaches and methods, we can get to a design of the battery using a green digital twin, what we are calling now for the waterborne sector, to convert the physical vessel orientation into a digital orientation, allowing the development of model-based control system and also the verification of the system interoperability. This brings me to some approaches for designing the battery, where a modular design can enable to scale up first the battery pack and meet the energy and power requirements for different applications. And here we are offering some solutions for modularity, which can be designed for fast charging, and also integrating innovative lightweight material and safety components. So this development is based on high reliability and safety, based on a compact design. Some solutions also are provided for plug-in and play mechanism for the vessels, where the integration will be more easier, assembly and disassembly also will be more easier. What Bring is offering here is a battery system design, prototyping and manufacturing, where we are respecting the 4R design about recycling, refurbishment, remanufacturing and reuse. So we propose some solutions to reduce the weight by 10%, fast charging capability with high voltage design, and also compliance toward safety standard with increasing energy density by integrating innovative lightweight material and safety components. And here in my picture, you can see some design without the thermal fuse and with the thermal fuse. And as you can know, the safety challenges in the marine sector, they are different from the transport sector. If a thermal runaway, for example, occur in the transport sector or in your car, you can run, but in the waterborne sector, when you are in the middle of the sea, it will be not possible. So that's why it brings me to the second topic, which is about advanced thermal management system solution. And here the idea is to increase the energy efficiency, lower the battery aging gradient, and control the heat temperature, or monitor and optimize the thermal status of the battery. This can be done by developing thermal management system to monitor and optimize this status and control the battery temperature. And this can be investigated by different approaches, air cooling system, liquid cooling system. There are also some hybrid solution. Another also idea is to incorporate some active safety materials such as the thermal fuses or contractors, and also connection to the BMS as well, or using predictive temperature evolution control. And here those solutions are already implemented in the waterborne sector. They are at higher tier level, and what we are offering here is the full solution to monitor and optimize the thermal status of the battery, a homogeneous heat distribution within the battery pack, and predictive temperature evolution control that enable fast charging services, for which the transport sector is going on now, and also the marine sector is going to. And at the end, we will have a low temperature evolution, predictive control, reliability, and also increased safety. So the next topic would be about advanced multi-scale and multi-physics model. So as I said at the beginning, you cannot design a battery without any control orientation of the whole system. And here the idea is to accurately predict the performance, thermal behavior, and also the lifetime of existing and future batteries, with high fidelity and multi-scale and multi-physics models. So as I introduced at the beginning, there are different levels, cell level, module level, pack level, and the system level. So the idea is to go from an idea or a picture about the battery to a design, to a simulation and the design of the battery, in order to go after that for the prototyping and manufacturing. This brings me to the development of accurate state of X estimation, and to discuss about also the BMS. And here we are using some machine learning methods and data-driven methods in order to estimate the state of charge, state of health, and we can improve the battery lifetime. The idea also is to shift the computational effort to the cloud by using cloud solutions, which can enable to reduce the computational effort, but in the same time can enable, with the huge data that we will have, that we will store, to have some real-time troubleshooting of the battery. And here, as I said, some data-driven model extracted from machine learning method are used in order to estimate the status of the battery. So just to go to conclude what I mentioned in this session. So the first idea is to, in order to design the battery and optimize the battery, we need to start by developing a modular and compact design. The idea is to reduce the weight because we are also limited in the space design in the ship. So we are here providing also some solutions that can reduce the components, cabling, piping, to allow the optimal use of the space on board the vessel with a compact design, and to reduce also the complexity of the system. Of course, when we are reducing the components and the cabling, we are reducing also the costs for the production, for the maintenance, because we are reducing the components, which is obvious. And modularity approach is the way to go through the electrification, because we need some approaches that can be adapted to different vessel types, different operation. And that's why we are developing modular and compact battery system design, of course, with eco-design approach, because we are thinking also about circular economy, assembly, disassembly at the end of their life. Then when I discussed about the thermal management, the idea is to control the vessel heating, cooling, increase the safety also of the vessel and increase the safety in the waterborne sector in general. So we need to put some mechanism to prevent the thermal runaway propagation in the battery pack and in the whole vessel. Now we are going also through some fire simulation to integrate fire prevention and fire suspension measures, but also safety can be increased through using some electrical and circuit protection measures. And the safety, of course, needs to be assessed from the battery reliability point of view to ensure that the system will deliver the required energy and power in all operation conditions. Then what would be also the challenge or the way to go through electrification of the waterborne sector is also to think about BMS or battery management system. And here it needs to be compatible with several ship type and operational profiles. We also need to extend the battery lifetime through accurate set of X estimation, because when we are talking about the sailing distance or range in the waterborne sector is higher than the range in the transport sector. And here we are using also some artificial intelligence techniques that can provide accurate state of X estimation. And this will bring me to the end of my presentation. So if you have any questions, please let me know.
Imane, thank you for your presentation. A very comprehensive one, scientific presentation representing the ongoing, all the time, innovation in the battery extension and optimization solutions for battery packs. It's continuous, I would say, innovative process in that sector. So we're really thankful for your contribution to see what is the latest. We don't have a question now, but please remain with us for any questions if they arise, and some short discussions.
Sure.
Thank you, Imane. And I would like to proceed further on the agenda. Now I would like to invite Thomas Gerritz from Helix to give us a presentation on the actual hyper-powered vessel battery charging systems, and as well to represent Helix and the range of your products and activities. And special thanks to Thomas for joining us on his day off today from Denmark. Thomas, you may start your presentation, and thank you for joining.
Hi. Good morning, all. Emil, thank you for having me to give this presentation about the hyperpowered vessel battery charging systems. My name is Thomas Gerritz. I work within Helix as a research and innovation manager, and thereby responsible for new innovations, system architecture, and looking at new markets in which we can explore to apply our technologies in. My agenda for today will be first a short introduction on what Helix has been doing up to now, which is mainly in the automotive markets. Then I will go to the megawatt scale charging systems that we have been installing up to now. Then specifically something on the marine and water implementations that we have implemented, and what our learnings and needs are in implementing charger to vessel interoperability as we do so in the automotive branch already. Lastly, I will explain some things about the Hyperbot projects, so hyper-powered vessel battery electric charging systems, and what our ambitions and goals are within that project. Okay, so shortly about Helix. We have a strong belief that going to electrification of transportation is a very good way forward in reducing greenhouse gas emissions. And we see that really as our mission to implement smart charging and management solutions such that we can electrify the whole landscape of transportation and every method in which that's been explored. Our strategy in this is really to supply turnkey solutions to our customers, which are completely tailored to their needs, but still based on proven high quality products. So the main challenge for us is to implement systems with reusing the same building blocks in the configuration required by the customer, and do so by using standard communication methods as are defined in the automotive conductive charging standards. Some numbers about Helix is, I think most important ones is that we ship more than 2,000 charging systems already, are active in a lot of countries. We develop our own power modules up to complete charging systems and turnkey solutions. And we're active in more than 10 research projects on local, national, and international levels. The markets in which Helix is active is mainly it started off in the public transport market for electrification of buses in big tender processes. That started off in the Netherlands and basically expanded to all of Europe and America at this point in time. Mostly some projects in Southern Europe. In Southern America. Port equipment, that I will explain something more in detail on later on. Commercial vehicles. Within the mining sector, we have there are automated self-driving vehicles that are being charged from the bottom side. The Copenhagen project, that's our main marine project that we did up to now, that I will show some things about. We're also active in the passenger car market, but I will leave that for now. The standard charging products that we offer are mobile products, our Flex series, the ultra-fast chargers and rapid chargers. For marine applications, mainly the ultra-fast charging systems are of interest because they can supply the power needs that we see now. But this is definitely increasing towards higher levels even than what we can supply today with our standard offers. So Helix really offers the complete development cycle. So we design in-house and manufacture everything with local partners. Important thing to mention here is that with ChargeSight, that's our back office system with which we can continuously look into charging systems, charging sessions, performance, and do energy management to ensure that not only the vehicles are charged properly, but also that the grid connections are remaining up and running, and we don't use more power from the grid than what's available. So the megawatt scale charging system, the trend is really going up. We started off with systems up to 600 kilowatts, but we're now designing towards much higher power levels because there are a lot of requests from the market in increasing power levels. Within the charging MCS task force, there's being looked mainly at truck charging and possibly aviation or marine charging afterwards, but that's really on standardizing a plug to ensure that cable charging is done in a standardized and very reliable manner. Within marine and mining, additionally, automated charging systems such as the one shown by Rainer are very useful to automate the charging process and to ensure that the available time is used really to charge instead of to make connections. So automating that connection sequence to minimize the connection times is really crucial there. As Helix, as I said, we implemented quite some megawatt scale charging solutions already. Important thing to mention there is that the solutions do not supply multi-megawatts to a single outlet, but the overall scope of the installations is definitely much higher than a megawatt. As you see, in Amsterdam we did a 31 megawatt installation in the Schiphol area. That's the Dutch national airline, and as you can see in the video, this is an explanation of our installation of the infrastructure in Wiesbaden, Germany, which was a 6 megawatt charging system installation. And here you can see what that would mean for a site, the amount of chargers that are being placed in order to charge all the individual buses. The charging poles you can see here in the middle all have a CCS connector that is used to supply the bus. It's similar to what's shown here for this truck. On board implementation, we did an implementation with PSA in Singapore, which was about installation of a 450 kilowatt fast charging system, which is being used fully autonomous with an automated coupler device, as shown in this short animation. So basically, the goal is that the self-propelled vehicles, which are completely autonomous, are also charged autonomous in order to have a 24/7 operation. The charging system is built into a 10-foot container to be able to be relocated quite easily, but also implementation of the system within the container is much easier because most of the work can then be done in factory instead of on site. This charging really goes according to the charging standards which are valid in the automotive world, so the conductive charging standard and also the ISO 15118 communication. Additionally, there's a real-time communication to the local PSA charge monitoring system and management system. Specifications of the charger here is set 450 kilowatts. It's a liquid-cooled charging system. So the internals of the container are fully isolated with respect to the external environment. Communication goes via the open charge point protocol, which allows us to feedback the information not only to the PSA port authority, but also towards the Helix back office charge site. Okay, then something more on the marine implementation that we did for Riva in Copenhagen. There, with a QCC3 connection system, ferry route of 90 minutes with 13 stops, 13 intermediate stops has been implemented. 7 ferries are sailing there, and on each end of the route there is a 600 kilowatt system installed to allow automated charging. And in this short video you get an impression on how that charging looks. Here you see the ferry go towards the Yeti. That's basically a floating pontoon on which the connector is placed, and this allows us for compensation of tidal movement without the need for of an actuator that compensates for that movement. Some more details on that. Basically, the whole charging system consists of the medium to low voltage transformer station with metering. Then our 600 kilowatt opportunity charging system, which you can see in the bottom left picture here. Then, of course, the automated coupler device, and here you see a picture detailing the Yeti, which is floating, and the ferry really connects here up to this hooks up to this point to ensure that the ferry is rigidly connected to the Yeti. overview of the charging system is that here you can see on the left side our 600 kilowatt charger that has an interface towards the QCC3 and to the Damen Wi-Fi interface. On the vessel side, of course, you have the complementary set of the socket, also with the Wi-Fi interface, and the onboard communication controller that basically is the translation between the charging process on Helix side and the onboard Damen control system. So basically here the Wi-Fi is used to ensure that once the charging system sees communicates with the vessel, that the Stabli pin is extended and the charging process can be commenced. Main challenges that we saw in this marine application using automotive products, because of course you're using a system that's initially designed for charging of trucks and buses and cars, and you translate that system towards use in a marine application. And since it has not been devotedly designed for this, some challenges occurred that we hopefully to further investigate in the Hyperbot project and to implement our learnings to further improve implementations there. One of the issues that we investigated in this system is leakage currents that are basically produced by both the charger and the vessel. But if the vessel is not connected to the shore side, then basically there's no path for these leakage currents. But once charging starts, you allow basically for a hull current to be transferred from the charger to the hull and then back through the water or some other return path, which can be a landing plate between the vessel and the shore. All kinds of options there, and the leakage current that basically flows through the ship hull, leading to corrosion, should of course be avoided. And in the Copenhagen implementation, we eventually achieved in doing so. And this has been verified by an external company. Another issue was communication, because in automotive the vehicle is always isolated with respect to ground, to earth, and that's not fully the case with a vessel. So because there is a potential difference there, communication between the two needs further, that issue needs to be addressed. And basically you need to ensure that communication stays up during the complete charging process, of course. And that has proven to be quite a challenge. So whether the automotive-based communication protocol is the most suitable there is still something to be investigated. Furthermore, we used the ISO 15118, which is basically the standard communication protocol between a vehicle and a charging system in the automotive. But in this case, not the Wi-Fi based communication protocol, which is developed for that, has been used, but basically proprietary solution which was developed by Damen and implemented together with us. So I think improvements can be achieved there. The tidal movement with a linear actuator, it basically requires that you use a floating Yeti, and I can imagine that in a lot of situations this is not favored. So basically also looking at different connection systems, such as the ones presented by Reiner, so the stem-on solutions will be investigated to see what has the best specifications in order to cope with tidal movements without limiting the system to certain solutions. The salt and humid environment, of course, within the automotive, charging system should also be very high uptime and robust, but they're typically not designed for the continuous environmental conditions that are present this close to the shore, and of course that also has price impact. So the intention is there to develop a system which can cope with the salt and humid environments, and that's definitely something different than what we have been doing in typical automotive implementations. Additional thing is that because the power levels for ferry and other vessel charging will only go up, as I previously explained, and this has additional requirements in terms of safety precautions. Going to higher currents also means higher short circuit protection requirements, and issues like that still need to be investigated and addressed when going to these multi-megawatt single outlet charging systems. So that's really something different from what we have been doing up to now in bus implementations. So to give you an idea on what we typically use in interoperability requirements between, for example, a bus or a truck and our charging system, this picture, it's maybe a little bit too busy, but basically what I try to visualize here is that we should try to prevent proprietary solutions too much when transferring the charging application from automotive to marine world. I mean, a lot of things have already been investigated, standardized, and that can give us quite a big benefit. And basically, for example, adding parts to the cold ironing standard, which is already there in the marine world, to learn a lot from existing standards. Ones that I really wanted to point out is basically here, the 61851 is the main charging standard for conductive charging between a charging system of ours, for example, and the vehicle. And within that, there are specific parts for EMC, for communication, and of course referring to safety requirements for both the European and, for example, the North American markets. Especially interesting in the automotive world is also the bidirectionality requirements, which I think are not relevant yet for the marine applications. But the idea there is that by having a bidirectional power flow between the two, also grid support can be given if at some point in time the grid has difficulties in keeping up, and because you have a lot of battery energy in vehicles, using a V2G bidirectionality can help support that grid. So if we would transfer this to an electric vessel, there are still quite some considerations that need to be investigated. For example, will we standardize the plug types that are allowed to be used, or will that be up to the customer and really dependent on the vessel type that they are charging? Will the same EMC parts be relevant, or is something additionally needed for electric vessel EMC requirements? Because it's as I said, it's not a fully floating system. It can have leakage currents which should be avoided with respect to the automotive market. So that's a difference. And also the communication, will it remain as we did in Copenhagen implementation? Will we go to the Wi-Fi version, which is also being used with an inverted pantograph, which is coming from the mast down towards the bus in the automotive applications, or will there be something totally different needed because the marine application requires so? To me, I really am in favor of standardizing at least the whole implementation, and of course that can't be the same solution for 1 to 20 or more megawatts, but at least standardized solutions should be used in order to avoid proprietary solutions, because basically then you're reinventing the wheel within each implementation, and that's something that we really would like to avoid. So standardized connectors has also been done in automotive applications. An example of a good cable alternative is the megawatt charging system, which is currently in development, and that's a good candidate up to something like 3.5, 3.7 megawatts. Okay, something more on the Hyperbot project. Here the intention is to really implement a full-scale e-ferry line from the island to the mainland in Germany, and the idea is there to develop and deploy a scalable multi-megawatt system with auto-connect device. So as shown here in the pictures, one of the solutions from Stenwell Hoptech will be used there. What and how and which requirements are needed for there are still to be determined. One of the main goals, ambitions of the project is to really provide a proposal towards the regulatory framework to come up with something, some connection and charging system that can be standardized in order to help the market work towards default solutions. The power needs on the mainland will be 2 megawatts, and at the island, the island grid is much less powerful, so most probably half to 1 megawatt system will be installed there. And basically that difference in power already requires us to deploy a scalable system to ensure that with the same hardware we can compose the systems of both island and mainland side. Ambitions of Helix itself within this project is to avoid proprietary solutions. So really to come up with a solution that's not only suitable for this port, but can be used throughout Europe and the world in order to make the solution scalable in terms of rollout. I mean, we as Helix like new projects, but we like to do them based on the experience we already had and not reinvent ourselves each and every time. So yeah, basically every second counts. Typically, there is a fixed duration at the port. So if the connection and initialization processes take too much time, basically that means that the power of charging only needs to be increased further because a certain amount of energy needs to be inserted in that vessel battery within that time. So it's really important that we have a fast and automated connection system, basically to minimize stress on the charging equipment. And that's thermal stress, that's reliability, that's lifetime, that's all directly influenced by the required power level that we need to apply. Yeah, basically within automotive, we are very experienced in delivering systems which have a daily operation reliability of 99.8%, and that's really something that, of course, we also strive for in this marine market. Yeah, as I said, a scalable multi-megawatt charging system. The concept is to come up with building blocks that can supply 1,000 volts, 500 amps, and then we can use multiple of those blocks to compose a charging system on either end of the line. And as I said, the interface between the charger and the coupler should also be standardized, such that we can, for example, shift between a boat type and a ferry charger type of coupling system, as Heiner presented. Changing the coupler type should not mean that the whole system should be different. So basically, also standardizing the connection between the charger and coupler helps us in easing the implementation and minimizing risks. That was my presentation. Thank you all for listening, and if there are any questions, please.
Thomas, thank you for your full presentation with a wide range of Helix services and products what we're seeing. We've seen the transport solutions for transport and also for maritime, and a great thanks for introducing Hyperbot project. As you mentioned earlier, we were quite anxious to start on the project, so we're doing this panel here within the days 22. Great presentation, thank you. Please stay with us if you can, and once again appreciated your time today.
Yes, I will. Thank you very much for having me.
Thank you, Thomas. Well, now I would like to move on with the last presentation from the first session for today. Unfortunately, we couldn't have Mr. Rampen, Peter Rampen from Damen joining us directly today due to the day off, as I mentioned, in Denmark, but we have recorded his presentation. His presentation is dedicated to the ship side, the different charging solutions for ships, the services for charging these full electric vessels, or also the hybrid options. So now we're gonna turn on the presentations for Peter, from Peter Rampen from Damen. Thank you. We are waiting for the presentation now.
Good morning. My name is Peter Rampen. I'm a Principal Research Engineer for Electric and Automation at Damen Central Expertise Center for R&D. I'm now going to start my presentation. I have more than 18 years of experience in maritime electrification, and before I joined Damen 6 years ago, I was already involved in the development of one of the first hybrid ferries and also in a hybrid superyacht. It's good to mention that I'm also member of the Dutch Committee for IEC standardization, and in this I'm also involved in the standardization for standards related to charging connections in the standards for utility ports, utility connections in ports. Today, I'd like to share with you some ideas we have about becoming making charging as a service available for ships. But I would like to start first with a small introduction of Damen. Damen is a family-owned company operating for more than 19 years in the maritime industry, doing design, new build and life cycle support of ships. Damen has a very wide portfolio, from naval vessels to super yachts, from small harbor workboats to large offshore vessels. The mission of Damen is to become the most sustainable and connected shipbuilder in the world. Electrification is one of the key technology enablers for this mission, and is now the only technology available to go to zero emission, so sailing without emitting greenhouse gases. We have already quite some experience with electric vessels, starting more than 20 years ago with electric propulsion, and since 10 years we also applying large battery systems on board that can be used for partially or fully electric sailing. This started 10 years ago, first in hybrid configurations, ships that sailing with still on generators but supported with batteries. But since 5 years we see also ships that sailing fully electric. That doesn't mean that the systems on board of those vessels are fully electric as well. Those can still be hybrids. As you can see on the slides, the available topologies you recognize probably also from electric vehicles. Of course, fully electric is very simple, but it can only be used for applications where with a predictable and limited load profile, and on locations where shore power is available. Although a hybrid is more complex, it has more possibilities and is therefore a good solution for many vessels. The choice of the topology has to be made early and depends heavily on the operational requirements and load profile of the ship. Batteries are evolving quickly, but compared to fossil fuels, they are and will never be as good with respect to energy density. Therefore, it's important to make an integral design based on energy. As you show on this slide, this starts with a good understanding of the operational requirements and load profile, but also the local power availability. Based on this, the choice can be made for an hybrid or a full electric topology, and then also the electric configuration can be selected. All this is focused on the energy availability in the batteries, but also the shore-side facilities have a big impact on the choice we need to make. A quick remark about the market. The market has, in the last decade, been grown significantly, as you can see on this graph. Currently, about more than 400 vessels are in service, and including the ones under construction makes about 544 in total, which is for now still a small niche, but exponential growth is expected, as also compared to the EV market. At Dame, we did till 2021 about 45 vessels, which is about 10% of this market, which is a significant market share in this growing market. Since electric grid differs from one location to the other, the location of operation is very important for the design. This influences the shore installation and might even affect the ship design. The business case is very dependent also on this, the local grid and energy prices. This makes it important to include the shore installation in our scope as well, as we do nowadays. What is shown on this graph are all the electrical building blocks that are required for electric ships, so from grid to propeller. During the rest of my presentation, I want to focus on the shore charging side. Starting to show you some examples to show you the state of the art of charging for ships. First example is this passenger ferry. The power and energy demand on these vessels is relatively low and is comparable with about 2 road buses. Because of the short time that the ships are on the quay side, the time for making the connection is very critical. Therefore, for this kind of vessels, we're using automatic connectors. As you can see in this animation, we're using a connector that is also developed for road buses and HEVs. And the charger in this situation is an automotive charger that is built by Helix, but also gave a presentation before me. At the moment, 7 of these vessels are operating in the city of Copenhagen. Next to the 7 vessels, we also delivered 3 chargers. At the moment, we're building 3 more of these vessels that will operate in the Netherlands. But they will not have an automatic charger, but will be equipped with a manual connector. Other example is a large ferry, a road ferry, and here the power demands are much higher, and for this, chargers are not available on the market. For this, we developed together with our partners a dedicated charging solutions. This includes also an automatic charging system, as you can see in this picture. In the presentation before from Stefan, this charger was already shown. The last example I want to give you is not a ferry, but an harbor truck that is close to delivery to our client. All the commissioning and trials have been finished, and now it's sailing from our building shipyard in Vietnam to our client in New Zealand. and then when at the arrival will go in service. In this case, the time for making the connection is much longer. So here we use manual connections, but to make this connection still manageable, we develop also our own cable management system. And for the charging connection, we use 4 CCS HPC connectors. These automotive connectors are water cooled and have a current rating of about 500 amps and can be used up to 1000 volts. Connecting a shore connection is not only hardware, it also involves communication and control and safety circuits. For the example, for the last example, we developed our own communication, control and safety standard, which we also apply in other vessels nowadays. This protocol is relatively simple and is still dedicated for our own vessels. To conclude on the state of the art, at the moment there are many solutions available. For ferries, automatic chargers are used, automatic connectors are used. For other vessels, this can be done manually, but every vessel, every location still has its own dedicated designed shore connection. In the future, if electric vessels becomes even larger and you want to be able to charge your electric vessel on different harbors, and with the same charges you want to be able to charge multiple vessels, of course standards are required. At the moment there are no maritime charging standards available, and to develop these takes years. So we think that maybe the automotive standards can be used in maritime domain as well, especially at the moment with the development of the megawatts charging system. The power levels becoming close to what we need. The levels will be about 3 megawatt, and all those protocols are ready to be used nowadays. Those include already all the communication and control we need, but this also includes administrative layers. And these protocols are ready for vehicle-to-grid functions. But implementing these standards in the maritime domain comes with challenges. I now want to give you a few of these challenges that we see. The first challenge is that the power ratings on vessels is much higher. So and on ships, because of the diversity of ships, the topologies are different as well. Every vessel has its own grid on board. Furthermore, we use much larger battery systems, which can consist of multiple strings and having at least 2 dedicated systems. For the power levels and amount of batteries, it may be required to have multiple connectors in parallel. And as last, the power management system on board the vessels is different than that is used in cars. So this also needs some changes. Another challenge we see is that the battery systems available on the market are made by different manufacturers, and each manufacturer has its own solution. And this includes also the battery management system, what is required for the communication. Also, the allowed or accepted EMC levels on ships are higher than that are allowed on cars or other vehicles. This can lead to interference, and wrong earthing can also lead to corrosion of the vessel, especially with DC charging. And the last example we see on the challenges is the safety philosophy that is different. As an example, on ships, it's still required to have emergency stops on the bridge and on the shore station. And this is not part of the standards in the automotive. To conclude, if we want to code for charging as a service, we need standards so that we are able to charge a vessel at multiple harbors, and with the same charger, you are able to charge multiple vessels. The maritime standards are not available, and we think that the automotive standards can be used for this. However, this comes with challenges, and maybe needs that the automotive standards need to be adapted for this or needs additions. We'd like to work together with the whole value chain to work on these challenges, and one of the projects we're going to work on is the Hyperbot project, which is an EU Horizon funded project. I want to thank you for your attention and enjoy the rest of the conference.
Yes, and I would like to thank Mr. Peter Rampen, even if he's not directly live with us, for excellent informative presentation covering the different charging solution and services for various ships. And I'm obliged to correct myself, 27th of April is the King's official birthday day, the King's Day, Koningsdag in the Netherlands. So thank you for the gents joining us from the Netherlands today. And with that said, we are now coming to the end of the first session for Innovation Days 2022. It was mainly dedicated to the Hyperbot project partners, and the project was approved and granted by Horizon program, and it's about to start anytime soon, and we're expecting it to start in June. It's to develop a hyper-powered vessel battery charging system, 2 full modular multi-watt recharging system in 2 European ports, which will aim to deliver it in the fast turnaround times of battery electric ships and easy charging of larger onboard batteries. So with that said, I would like to break now for a short coffee time or tea time, whatever you prefer. And please join us again at 10:40, so in 10 minutes time, to continue with the second session of Days 22 webinar, the OPS systems for different ports and solutions for ships. Thank you, and see you in 10 minutes time. Good morning, dear colleagues. Welcome back to the second session of our InnoDays 22 webinar today, Charging, Storage and OPS System for Ships and Ports. We'd like to proceed further on with the session dedicated to OPS, and to mention once again our partner for today, it's the Baltic Ports Organization. And presentation will be given by Mr. Bogdan Oltakovsky, Secretary General of Baltic Ports Organization, and the topic will be on the Baltic ports for climate and the actual role of onshore power supply infrastructure in this initiative. Bogdan, you may start your presentation now if you are ready.
Well, first of all, I mean, thank you very much for inviting me to share BPO point of view on OPS, but maybe also in general on the climate challenges for ports. I have prepared a quite short presentation, so let me just start with it. I hope it would work.
Yeah, it's full screen now.
Okay, thank you very much. So maybe just to start the presentation with a short introduction of who we are. BPO is the network of the Baltic ports from all countries around the Baltic Sea, except Russia. Recently, we have around 50 members, and our office is in Gdynia, in fact, but we are registered in Estonia. Our mission is to contribute to sustainable development of the Baltic, of the maritime transport and ports in general. And by doing this, we believe that we are strengthening the competitiveness of the whole region. And here you can see the photo, nice photo of our chairman Kimonaski from Port Hamina Kotka. Yes, and I'd like to go on, and something stopped. Sorry, I have to start again. Yes, so I'll talk about challenges for a while, then I focus a bit on Green Deal and Fit for 55. I will give a few slides about the regional cooperation and our initiative called Baltic Ports for Climate, and I will end with some conclusions. So maybe I would start with the main challenges for the ports. Of course, ports are just part of the transport infrastructure, and ports must face the challenges that are the same for many players. And one of these main challenges, of course, the climate change and climate policies, climate regulations, and how we respond to those challenges. And for ports, one of the main issue for next decade is how to be able to reduce emissions, greenhouse gas emissions, and how to be prepared for greener fuels. And one of these is, of course, OPS in the ports. I'll come back to that in a bit later. So I just would like to give you a few examples, but I know that there will be a presentation from Port of Helsinki and Port of Malmö, Copenhagen later on. So I won't go to the details, but just to underline that ports are now having their own strategies how to become neutral or how to reduce CO2, yeah, and in what time framework. And this is just the example, Port of Helsinki. And you can see also that one of the actions is to invest in onshore power supply. And this is a case of Port of Helsinki. A similar case in Port of Stockholm. They also working hardly to reduce greenhouse gas emissions and also investing a lot in onshore power supply. Similarly, in Port of Tallinn, they have also did a lot of investment in onshore power supply, but also they decided to use only renewable energy sources. And you can have many other similar such examples in the Baltic ports. And then, of course, we have a European Green Deal that was presented. It was more than 2 years ago already, or even maybe 3 years ago. And we all know the main goals. The main goal is to become neutral, climate neutral in year 2050 for all European Union. And also the goal in between is to reduce emissions by 55% by year 2030, comparing to year 1990. And this is, of course, not easy. And as you know, European Commission has presented the first package called Fit for 55. And one of the measures they proposed is to make ships, passenger ships and container ships using OPS, and at the same time, ports should invest in onshore power supply in berths for this kind of ships, so passenger ships and container ships. And we have made a detailed analysis of this piece of package or specifically the regulations proposed. And we did have some comments. We sent it to the European Commission, and we are of the opinion that investing in OPS is only only makes sense when it is economically feasible. So if you have only a few calls per year, it's not really economically feasible. So that's the first comment. The other comment is that you can, of course, have onshore power supply in ports, but the main question is what about the energy sources in the country that supplies onshore power supply? If the energy is produced out of coal, maybe it doesn't make sense to invest in onshore power supply right now. Maybe we have to wait, or not maybe, but logically we would rather wait until we produce energy out of the green sources. And then we also commented this piece of legislation in a sense that quite often in ports you theoretically can supply energy, but you have to also look at the network. You have to look at the investments you have to make in providing so much energy into the ports. So it's not just OPS in the port. It's more larger, broader context. But going further, I'd like to present you a few examples of the regional cooperations. Nordic Council of Ministers started a kind of a project, I think 2-3 years ago, to kind of stimulate the development in Nordic region, including Baltic, and they have prepared so-called roadmap for sustainable cruise destination in the Greater Baltic Sea region. And there were a few seminars, conferences, also with politicians. So they wanted really to make one move forward, give some impulse for industry, but also for administrations, for politicians in the region. And they came up also with some assessment how to finance such investment in ports. They produced such a report, and these reports are available. So if anyone is interested, I think she or he can Google easily. If not, I welcome you to contact us and we can provide this information. Then quite recently, at the beginning of April, there was a meeting of 36 cruise lines in the Baltic, and they have signed a memorandum of understanding, and they committed themselves to use OPS in Baltic ports as soon as possible, but not later than the year 2024. Again, it is important to build onshore power supply in ports, but at the same time, it's very important to make sure that ships coming, cruise vessels coming to the Baltic ports will use onshore power supply. And then, of course, the cooperation between the ports. The number of ports with OPS is growing quite quickly, quite rapidly in the Baltic. And this is due to of course, their own motivations, their own investments, but also quite often the Baltic ports are creating a consortium, 2, 3, 4, 5 ports getting together and applying for co-funding from European Union, from CEF fund, in order to speed up the process and also help financially to make this investment available, OPS available in the Baltic ports. But at the same time, we still see a need for the cooperations, and we have started the initiative called Baltic Ports for Climate, and we want to make a consortium of a number of the Baltic ports, but also with other stakeholders in the region, in order to be prepared for future onshore power supply, not only in passenger vessels, but also for container vessels. This is also a part of European Green Deal, and we think that there are quite a lot to be made, not only for passenger ports, for passenger vessels, but also for container vessels. So we are now working, we have already initiated some contacts, and we are planning to make this project happen. That means that we would make the consortium and ask and deliver the application to European Commission to co-finance such an initiative. Maybe at this point it is worth to say that of course the money is important, and it's a huge investment in ports. But from the other hand, if you make such umbrella projects, it also makes ports working together and also exchanging the information, seeing those investments in different places, and it always helps ports to go further and discuss main challenges, and also trying to maybe adopt a solution that is already available in one port to another place. So such projects also added value, not only financially, but also because there is exchange of know-how, experience. People are seeing those investments in different places. And as I said, we will ask European Commission CEF to fund for co-financing, and we are expecting the next call to be open this autumn. And just coming to conclusions, yesterday I saw the new report from McKinsey company, and it is clearly said that world is electrifying. So there will be more and more electric propulsion used in vehicles, but also there will be more and more electricity supplied to ports. So the world is electrifying clearly. So are the ports, and we can see that the number of OPS is growing everywhere, especially in the Baltic Sea. So OPS now is mainly available for passenger ships, but next there will be container ships to be obliged to use OPS, and probably in the next future the other type of ships like dry bulk, liquid bulk, other types of ships will be also equipped with the facility to use onshore energy for the use when they are berthing at ports. But there are many challenges, and one of them is, of course, how to get finance, how to get money for all of this investment. And OPS is not only the solution, there are also other solutions. So port are working hard to get zero emissions, or to get climate neutral in next years to come. So with this few conclusions, I would like to finish my short presentation, and just to underline that we always, Baltic ports, always see the Baltic port industry here as the industry that are paving the way, that are getting green, and they are a good example for other ports around Europe, but also worldwide. So we keep going in that direction, and the number of OPS in the region is also proving that we are really green and going to the climate neutral direction. So, Emil, thank you for the invitation.
Yes, Bogdan, I would like to thank you for the presentation and for the support of Baltic Ports Organization, as always, on such a matters. Thank you for the comprehensive presentation on the BSR ports and OPS and general environmental initiatives and matters. We've seen on numerous occasions excellent collaboration between the ports in the Baltic Sea region on such initiatives. Would like to actually ask you one question. In this fast changing now current environment, we've got geopolitical and ecological forces are affecting all this development, I would say, of the alternative fuels and energy solutions in the maritime and shipping sectors. And will you be able to share some insights? We know how fast is everything changing in Europe and in the Baltic Sea region. Is there any feedback coming, any direct comments from the port that they're experiencing something even worse than what was COVID for 2 years? What is the current situation, if you can share with few words? Is it affecting this path which was set for alternative fuels, introduction of infrastructure and OPS and so on?
Well, the question is quite broad, but of course, what's going on now in Ukraine, the war in Ukraine, and the Russian aggression in Ukraine is terrible, of course, and every person on our side is aware of the terrible situation in Ukraine. But of course, it also has some consequences for energy supply, security supply, and you can see even yesterday or today that Russia just cut the export of gas to Poland. At the same time, we can see that there are new investments coming to the Baltic ports. I mean, LNG terminals, just in order to get the other way to supply economies with gas, not from Russia, but from the other sources. So there is a lot of consequences for energy sector and for the ports, of course. But when it comes to green energy, to new fuels, to climate impact, I'm expecting that this development would would go even faster now, because of course, if you would be able to supply energy from green sources sooner, then the sooner you resign from fossil fuel, and we are very much dependent here in Europe on Russian energy sources. So, in my opinion, there will be a even faster development now with green energy sources also for ships. In saying that, there will be even a speed up of investments in that sector, in ports as well. So that's my first understanding of the whole situation in Europe.
Well, thank you, Bogdan. Thank you for updating us on the current situation, all your feedback, what you're receiving from the ports in the BSR, and your opinion, personal in the situation. Well, yes, we will experience probably different factors favoring more other fuels, and again, LNG is coming as a big player in the picture. But as you said, it could stimulate, this challenge could stimulate the development of electrical charging solutions, electrification, and green energy introduction in the maritime sector. Thank you once again for your presentation and for support of BPO, and I would like to move forward on our agenda. We will have a presentation now by Monika Rozmarinowska-Mrozek from Akcja Forum, and starting from the OPS ports and their solutions and ships which are coming to the shores. We will now see some of the OPS opportunities for EU funding programs. So, Monika, please, if you can start your presentation and give us some more clarification on the different opportunities for EU financing. Thank you.
Yes. Good morning, everyone, and thank you for invitation. I will share now my screen. Okay, I hope
yes, it is full screen.
Okay,
yep,
okay. All right, so yes, so today I would like to say a few words about funding possibilities, opportunities in EU funding programs for onshore power supply projects. But before, just a few words about my company. I'm a consulting project leader at Akcja Forum. Our company specializes in providing consulting services, event organization, and communication. And one of the pillars of our activity is inter alia preparing applications for EU projects, and especially under the Connecting Europe facility. So yes, so to move forward and say and just give a short insight into the EU funding suitable for OPS projects. I must say that the main program that offers the funding for OPS, it's actually Connecting Europe facility. And under this, the funding period, the present funding period 2021-27, there are four main type of calls under which the OPS project can apply. These are projects on core network, where where ports from core network can apply with its projects. Project on comprehensive network, where comprehensive ports can apply. Another possibility is to apply under call connected with actions related to sustainable and multimodal mobility, and the exact priority under which OPS can apply its motorways of the sea priority. And the last opportunity under the CEF facility are calls dedicated to alternative fuels infrastructure facility. So a little bit more about each of the option. So the first option, project on a core and comprehensive network. Here, the projects, studies project and work projects can apply, and such projects should last not more than 4 to 5 years. The funding rates for studies is maximum 50%, and for works it is 30%. And for projects from cohesion countries, this funding rate can be even up to 85%. Generally, the projects of any budget are applicable. However, in order to ensure efficiency of e-funding, applicants are recommended to submit the applications project with a total requested EU contribution to the eligible cost not less than 1 million euro. It means that it is recommended that the total budget of the whole project should be not less than 2 million euro for studies, 3 million euro for works, and for project in cohesion countries, not less than 1.2 million euros. So it is the possibility for core, for comprehensive network. Here, the single port can apply, or also there is a possibility to make a joint application proposal with several ports and group some project from several ports into one. And also apply under one proposal. The second option, it is under motorways of the sea priority. Here we have only the general envelope, which means that there's no possibility to have a higher rate for cohesion countries. And what's the most important in this motorways of the sea? Such project should involve at least one core port and from the one member state, and another core or comprehensive port from another member state, and they should have the regular connection with each other. In the present financing period, there's no possibility to apply with OPS project under so-called wider benefit actions. So yes, it is needed that these two ports which would like to apply under motto of the Seas project should have a regular connection with each other. Here also the studies and works are possible to be financed. Similar, actually the same co-financing rate applies as in the previous call which I described. So for studies it is 50% and for works 30%. And the budget is also recommended to be not less than 2 million euro for studies and 3 million euros for works. And the third option that is possible under Connected Europe facility is to apply under coal connected with alternative fuel infrastructure, the facility zero emission. And this calls differ a little bit from the calls that I described previously. First of all, under this call, only works projects on, so real investment are only applicable, so no studies. What's the second thing which is different, it is that AFIF call, it is a blending call, which means that only the AFIF only fund project based on blend or a combination between EU grants and financial support from a financial institution. This financial institution can be either a EU implementing partner, which is, for example, European Investment Bank or some national promotional banks, or it can be also financed by non-implementing partner, which means just some private banks. But this blend is required. Such project should last not more than 36 months from the respective cutoff date. And apart from the infrastructure, from possibility to apply with project concerning infrastructure in port infrastructure facility, OPS facility in ports, there is also some possibility for co-financing some part of costs concerning vessels or port vehicles and equipment. But this eligible cost shall be limited to the just the difference in cost between a fossil fuel and zero emission vessel and port vehicles or equipment, and this difference should be regarded as the difference in propulsion system costs. And here we have the co-financing rate at the level of 30%, and the higher rate is possible for investment in cohesion country, and then this rate can be up to 50%. So a little bit about the dates. In the case of this alternative fuel calls, it is multi cutoff date calls. So the several calls are already the deadline for these calls are already known, and the first call is already closed, and the submission date was in January this year. And now the second call for AFIF is open with the deadline 7th of June. This year, another one will be open and with the deadline in November, and the two other calls are planned for the next year. In the case of the other calls concerning project on comprehensive ports and motorways of the seas, the first call is already closed, and the deadline was in January, but the second call is expected to be open in the autumn this year, probably in September. So yes, so as I said, the Connecting Europe facility is a main program for funding the OPS project. So there are just three calls where when you can apply with the OPS project. However, I just want to say just few words about other alternatives. The first one is Horizon Europe, but this program is mainly focused on research and innovation. So there are rather chances for funding research and development project, but also some proven commercial products are also possible, but it depends on particular calls. In the Horizon Europe, calls are typically announced with 3 to 6 month notice. And the another possibility where some possibility can be found is Interreg program, European Regional Development Fund, but here on the contrary, the scheme focuses on cooperation, collaboration, and community engagement, and the calls are announced typically by demand during the budget period. And in the case of this Horizon Europe or Interreg, you have to follow the announcement of calls and search for opportunities because there is a different structure than Connecting Europe facility. But some opportunities can appear. So yes, so thank you very much. This was just a short insight for opportunities for OPS project under EU funding programs. So thank you.
Yes, thank you, Monica. Thank you for the informative presentation on the concrete steps, what is available now and in the short and the long term for the stakeholders, for the ports, for the ship owners to see how they can aim and deliver their strategy. Dedicated to OPS infrastructure, of course, for charging solutions in the ports as well. Thank you, Monica. We don't have questions from the audience for now. And I would like to proceed now to the final stage of our event and to the conclusion of this session, now coming directly to the actual case studies, as we started from a picture from the Baltic ports and how is proceeding the deployment of such infrastructure, electrification of the ports and ships, and now going to the actual solutions, how it's been delivered in the Baltic Sea region ports, And now I would like to invite Mr. Andreas Slotze from Port of Helsinki, who is actually going to give us information on some of the solutions, OPS infrastructure in the Port of Helsinki, the challenges they've been facing and opportunities that is giving or you should give in a short or long-term future. Andreas, if you're with us, you may start your presentation now. I think I can see, yeah, Andreas is here. So yeah, we can see the presentation. Andreas, we've seen the presentation, but we cannot hear you. Just bear with us for a few more seconds, please. We're trying to rectify the microphone option for Andreas Slotze from Port of Helsinki. Yes, it seems to be an issue which we're going to definitely rectify soon. I'm wondering now if you can jump to the similar presentation from Port of Copenhagen, Malmö. Nikolai Haubre, are you available? Are you with us to give us the presentation now? And then we will return to Port of Helsinki afterwards, after we sort out the microphone problem.
Yeah, I'm ready. Let me just...
Yes, okay. Nikolai is ready to step in. Yeah, please. So now, please, if you can start sharing your presentation to see that it's working.
Yeah, then Andreas just have to
Sure.
start the presentation. Can you see my presentation or my screen?
We can see you, but if you can please try to share your presentation.
Oh, sorry, forgot to click the button.
Okay, excellent. Thank you for stepping in, Nicola. Please give us a presentation on the bringing the OPS to Copenhagen. Thank you.
Yeah, thank you very much. I'm going to talk about a bit about how we are bringing shore power to Copenhagen. But first of all, a little bit about who Copenhagen Malmö Port is. We are a port that spans two countries. We merged in 2001, Copenhagen and Malmö Port, when the Øresundbro opened. We're a full service port, and we're also a core port. We handle all types of ships and all types of goods. In 2019, CMP received around 340 cruise ships with over 940,000 passengers. We are owned partially by City and Port Development Company, which then again is owned by the Danish government or Danish state and the City of Copenhagen. Then we're also owned by City and Malmö. And something special about Copenhagen Malmö Port is that we're partially private owned, and we also operate the cruise port in Visby. Some of our facilities are shown here on the map. Malmö down at the right-hand corner, mainly focuses on cars, rail, and bulk. Visby, as you see, has only cruise, and Copenhagen is mostly bulk, container, and cruise. And we're going to focus on bringing onshore power supply to the cruise ships and ferries in Copenhagen. And in Copenhagen, we have three cruise locations: Oceankaj, Langelinie here, Oceankaj and Langelinie, and then we have a small location here at Nordertolbod. We're focusing on, for the cruise part, shore power for Langelinie and Langelinie over here and Oceankaj over here. Some general information about shore power in Copenhagen. We have shore power for the DFDS ferries that sails from Copenhagen to Oslo, and they're in operation now. I'm going to talk a little bit about them later on. And then we have the shore power for cruise ships, which is currently under development. We have three main locations for this. We have the grid connection inside the center of Copenhagen, right here. So we have to get the power all the way in here. And that's around 6 kilometers out to the converter station and the connection points out at Oceankaj. Then we have connection point over at the Langelinie. So we have to get cables or power all the way from the converter all the way over here, which is about 4 kilometers. So some information about the shore power for the ferries. It's a collaboration between DFDS and CMP. We design, build, and also maintain the system. DFDS is the sole operator of the system, and they buy the electricity directly from the grid, and they buy it with a green certificate. So it's either wind power or hydropower or something in that case. We started construction in September 2020, and we got delivery of the switch gear and the container where everything, all the technical aspects of the system is housed. We got delivery of that in July 2021. We switched on power for the first time in August 2021, sorry. And we tested it from August till October. And during the test period, we saved around 47 tons of CO2 and reduced diesel consumption while the ferries was in port by 105 cubic meters. The final, the inauguration was on 26th of August, and it's the first shore power facility in Copenhagen. Some technical specification of the system. It's housed in a 40-foot container, which you see on the lower picture, and each ferry have one connection point. So we have 2 connection points, which is fixed cable system, and they're specifically designed for the DFDS ferries. The system can deliver up to 2.8 megawatt, which is around enough power for around 700 houses. It's a flexible grid connection, which means that in case of a power outage in the grid company can shut off power to the system and divert it to more critical parts of the electrical system, for example, hospitals and power plants and so forth, if they need to restart those. The total investment of the DFDS shore power system was approximately 2 million euros, and it was funded by NEAR with 20% of the total investment cost, which is 400,000 euro. So a little bit larger system, the shore power system for the cruise. First of all, in 2020 or 2019, the City of Copenhagen, City and Port Development, and CMP went into a partnership to ensure green solutions for all port operation. But one of the larger part is the shore power system. And right now the setup is that the City and Port Development will construct the OPS system. We have made extensive studies for the last 3 years. We handed over the system, I believe, the end of last year to City and Port. And after this, when the system is done, CMP will take ownership of the system again, and we will be the end user and operator. Therefore, we buy the electricity from the grid and sell it to the cruise ships. And the reason why, I'm also going to talk a little bit about this later, but in 2019, a study made by Aarhus University showed that the cruise ships emitted over 18,000 tons of CO2, 300 tons of NOx, and 12 tons of particles. Compared to this is more than some of the most congested roads in Copenhagen. So this is a large contributor to emissions in Copenhagen. We have identified 4 major parts of the system. So in order to build this, we've looked at the grid connection, the converter, which we need to convert from the European grid, which is 50 hertz, to the cruise ship's 60 hertz electrical system. Then we have connection points on the quays. And then we have the cable management system that brings power from the shore to the cruise ships. Some of the more technical specification of the system in Copenhagen. Initially, we're going to build a 32 MVA system, which then later on we're planning to upgrade when more cruise ships are ready to receive power to a 48 MVA system. We're going to take a 30 kV high voltage cable from the grid out to the converter station. And just to put this into perspective, this cable can supply enough power for around 11,000 normal houses in Denmark. And then again, we're going to convert the power from 50 hertz to 60 hertz. And we're going to take 3 cables, so we have the opportunities to further expand Langelinje. 3 also high voltage cable from Oceankaj to Langelinje, and each cable can supply enough power for 3,500 houses. Initially, we want to make 3 connection points at Oceankaj and 2 at Langelinje. And later on, again, when there's more ships ready to receive shore power, we can upgrade it to 2 additional points, one at Oceankaj and one more at Langelinje. We're also gonna, first of all, buy 4 cable management system. So the plan is to have 2 at the Oceankaj and 2 at the Langelinje. And this is also gonna be a flexible grid connection. Some of the challenges we have faced in bringing OBS to Copenhagen is, first of all, why do we need to invest in shore power? As I mentioned earlier, it's one of the major contributors to emissions in Copenhagen, and we see that we have residential buildings really close as neighbors over at Langelinje. They're literally across the road. And out at Oceankaj, we see within 5 to 6 years, we will have the residential buildings right next to the cruise terminals. Of course, COVID-19 have been a challenging factor because we saw that it was very unpredictable the last 2 years. And as I show my colleagues from Helsinki would agree in that we saw the calls of cruise ships turn from quite a lot to 0 in overnight, basically. So, but we saw this as we still saw shore power as basically as a license to operate. So we looked at scaling down the system from a 32 MVA system to a 16 MVA system, and reducing the number of the cable management system, and basically just have 1 connection point at Oceankaj and 1 at Langelinje, so we would be able to receive ships and plug them into shore power. And of course, financing and funding have been a challenge. We've been fortunate enough to look at and be able to buy the electricity without tax. So we have gotten a tax exemption, but since we're also a privately owned company, we can't really just go into a project and say we want to build this and we have to, what's the name, English name, in lack of a better name, just set a lot of money to the project and say we need to show our owners that we can either go make a zero amount of profit or make a little bit of profit on the project. And as effect of this, COVID-19 also played into this, making it more unpredictable, the business case. I'm also going to go in a bit more into depth with the financing and funding of the cruise, especially the cruise part of the shore power system. We also looked at how we achieved the right setup in order to build this system. We saw that potential suppliers of the converter parts and cable management system would have little to no experience working with Danish grid companies, and we saw that especially during the construction of the DFDS system, and the company that did it is a very competent company, and we've been having a really good project. But we saw there's some differences in working from Sweden and Denmark, so we decided to split up the project into two sub-projects. I'll also talk about how we are going to do this a little bit later on. So if we look at the financing and funding of the cruise project, the total investment cost will be around 15 million euros. And we also got INEA funding of 20%, and we can maximum get for this 3.5 million euros in funding. As I mentioned earlier, we got tax exemption on electricity. This means that we can buy it at a much lower cost and sell it to the ship at a lower cost than what we normally could buy it directly from the grid. The financing is done in collaboration with the City and Port, INEA, and the City of Copenhagen. And the City of Copenhagen is expected to give a loan for the project. But right now we are waiting for the Danish Parliament to approve the bill to make this possible. Hopefully they will approve the bill within the end of 2022. In order to repay this loan, we will repay it through the operation of the OPS facility and the sale of electricity to ships. So the two sub-projects of the cruise shore power system is going to be the converter part. It's going to be a design and build contract with an open design, where we send out technical and operational specifications of the system, and then tenders can submit their offers on how to solve these problems or technical specification. And this is aimed towards more general companies that always or already is in the market for shore power for cruise system. For example, PowerCon or Actemium or so forth. And this project covers the converter station, connection points, and cable management systems. The other part of the other sub-project is the supply cables and grid connection. It's also a design and build contract, but with a closed design, and where we, or together with City and Port, make a technical solution, and how the minor details or how the details of the project is going to result is up to the contractor. This is aimed towards more general contractors who have local knowledge of working inside the City of Copenhagen and with the grid owners. This covers the grid connection and the cables between Langelinje and Oceankaj. Finally, if we look at the time and activity plan for when we expect to be able to supply shore power for cruise ships. At the moment, we're a little bit behind of sending out the tender for the converter part. Other than that, during the supply cables, we're right on schedule. But we expect to send out a tender for the converter station in mid-May. And as you see, we expect to have handover and final operations for the shore power system for the cruise ships in June 2024. Thank you very much for listening.
Yes, Nikolai, thank you for stepping in and for the excellent presentation, informing us what has been going on in a Copenhagen Malmö port, and how is your plan for the development of the OPS in a short term. I think I have a couple of questions here seen on the YouTube channel, and after that we will continue hopefully with Andreas Lotze to try the presentation again. Have you studied how much the noise reduction will be with OPS? It's a question from Matthias Sandal.
Yes, we actually have first-hand experience from the DFDS ferries. So both we have theoretical analysis from the cruise ship, but we have practical knowledge from the DFDS ferries. Basically, just to put it into perspective, Langelinie and the DFDS ferry is located around 200 meters from each other. So we practically reduce the noise and vibrations from the ship to zero. One of the main differences between the DFDS ferries and the cruise ship is that the DFDS ferries has a little auxiliary engine for heating. So that makes a little bit of noise, but for cruise ships, it'll be when they're connected to shore power, reduced to zero.
Okay, and actually we've seen another question here. Hello. Nikolai, I'm sorry, but I couldn't hear you.
Sorry?
Yes, I've got it now. Okay, it's another question. If you can have a look now, I just forwarded it to you. And it's any estimates what you could be the ratio between the peak power and energy quantity of shore power delivered to ships from one connection? For example, the energy from one Copenhagen 2.8 megawatt connection.
Well, this is the maximum rated connection energy. It's mostly because the grid in Copenhagen doesn't have so many amps in it, so we need to transform the power. This is done through the relatively large transformer in the DFDS facility, so we need to transform the power. But when they're connected, this is the initiation that take up that much power. There's of course a safety margin in this. I can't remember the exact figures, but I think when they're doing operation, I think we're around 1.9, 2.1. Something like that, depending on the ferries. There's a little bit of difference between the two ferries, the DFDS Crown and the DFDS Pearl.
Okay. Thank you, Nikolai, for answering the questions on the spot and for your presentation. Excellent to see the development in Copenhagen Malmö, and we hope to stay together in a joint BSR project in the future. Thank you.
Thank you.
Now we try to come back to Andreas Lotze from Port of Helsinki to give us the latest on the OPS infrastructure in the Port of Helsinki. Yes, we can see you, Andreas. Please, can you try now?
The big question, can you hear me?
Yes.
Excellent. Super. Yeah. Good morning, everyone, and thanks for having me. I'm really sorry about the technical trouble just now. I restarted everything and then it works again, Who knows about these things sometimes. Can you also see my presentation, Emil and everyone?
Excellent. It's a full screen. Please go ahead. Thank you.
Yes, super. I'm going to say a few words about OPS and OPS infrastructure in the Port of Helsinki. we've been doing the past few years and what we're trying to do in the future. In our strategy, current strategy, we stated that we want to be considered a sustainability or sustainable development forerunner. And that, of course, means doing more than the bare minimum. Maybe the main project, the crown jewel, so to speak, of in our sustainability strategy is our carbon neutrality program. And there we very early decided that the carbon neutrality program cannot only focus on the port of Helsinki alone. It needs to focus on the whole harbor area, because it would be intellectually dishonest to say that the port is carbon neutral if you haven't considered all the emission sources in the port. So that's why what we started doing back in 2018 when this strategy was formulated. And quite quickly, you notice there's a few main emission sources inside a harbor, and the largest, of course, is the vessels by themselves. Their movement in port-owned waters, maneuvering, and then you, of course, you have the at alongside, as we know, vessels use auxiliary engines for electricity production and also for heating. This is important, especially up in the colder parts of the world. About 80% of emissions stem from vessels in the port of Helsinki. Only about 5% are the port's own, and then you have the heavy machinery and heavy traffic inside the port area that makes up for the rest, about 15%. So, of course, we focused a lot on our a lot of our energy is going into looking at the vessel side because of its large relative size of the emissions, and technology can be a big help. On the left-hand side, you see the OPS connections, or one of the OPS connections, I should say, for the Helsinki-Stockholm route. And on the right-hand side, you see auto-mooring systems used in the Helsinki-Tallinn route, where it's very frequent liner traffic. So automatic mooring, actually, it only saves a couple of minutes on every mooring operation. But when you have the vessels coming multiple times a day, those few minutes actually they contribute to very large emission savings on the sea part of the voyage. But those emissions we don't take into account in our own carbon neutrality program, because the savings don't happen inside the harbor, they happen at sea. But I wanted to mention this nonetheless, because they are so significant. Well, so then going into actual OPS, here we see a picture of downtown Helsinki. With the exception of our cargo harbor in Vuosaari, all our harbors are situated very close to downtown. So this, in addition to carbon emissions, you also have emissions that affect air quality, and then you might have issues with noise. We've been lucky in that aspect that we don't really have a problem with that, but still. So there are multiple reasons for installing OPS. So here we have the two OPSs installed in the South Harbor. So with these two, 100% of the liner traffic between Helsinki and Stockholm is able to connect to OPS while in harbor. So this has been a huge step for us. And talking about the emission savings, these two combined, actually, the carbon footprint that our investments have made possible is actually larger than the carbon footprint of the whole of Port of Helsinki. I mean, our own direct emissions. So these two, with just two, let's say still expensive, but with only two investments, the carbon handprint is larger than the carbon footprint. So this, I think, is pretty cool. Here we have the Western Harbor, again, as you see in the background, situated very close to residential areas. And on the left-hand side, you see the city or part of the city called Jätkäsaari that is being converted from an industrial area to a residential area. So we will actually have residential buildings very close, actually right up to the quayside on the other side of the small basin there. So here we are. We have installed now auto mooring. It's operational on both sides of the terminal. And we're doing onshore power for both sides as we speak. This is going to be completed in August this year. So actually very soon. Well, just a few pictures. It's going to be about the container-sized equipment room, and there we see the foundations being made, and a picture of the crane. So this is also moving forward very well. These connections and the one in South Harbor we have designed ourselves, but I'll talk a little bit more about that in a couple of minutes. These are sort of fairly straightforward since you have liner traffic going back and forth between two ports. So you have the same vessel or a same couple of vessels every day. So it's a lot easier to tailor this solution to the actual traffic and the actual demands of the traffic. Here we see Vuosaari Harbor, our main cargo harbor, situated about half an hour to the east of downtown Helsinki. And there, hopefully we'll be able to finish also this year an OPS for the liner traffic between Helsinki and Travemünde in Germany. Same type again of setup as the previous. You have the same vessel type coming every day of the year, with quite a long layover time in port. So the longer the layover time is, then of course the more sense you can say that the OPS investment makes, because you can accomplish more emission savings if the layover time is long. And also I should point out that all these vessels that I've shown so far, they are fairly large, over 200 meters long. I think almost all of them. So they do use up a bit of energy while in port. So that's why these are good cases. We've also made the decision to only use carbon-free electricity in our OPS with the intent of moving into fully renewable energy sources, hopefully very soon. I should also mention that now what I've shown up until now is 5 OPS connection points. We have the 2 for the Stockholm traffic, and then we have the Tallinn traffic in Western Harbor, and here we see the traffic to Germany. 5 OPS connections might sound like it's not that much, but the funny thing is that pre-pandemic we had about 8,000 ports or calls per year. Back in 2019, I think we had about 8,000 calls. But with only these 5 connections, we actually cover 54% of all the calls that come to Helsinki. And this is because, again, the nature and the setup of the traffic that I already mentioned. Very frequent going back and forth. So these that I've shown you now actually make up for a surprisingly large portion of all our calls. Here in the middle of the picture, we see the container harbor on both sides of the same basin. And I put a question mark there because there are still quite a few unanswered questions regarding OPS for containers, and this stems mainly from Fit for 55 package that is about to be voted on in the European Parliament, I think now in the summer. As you may or may not know, at least the Commission proposal includes quite strict onshore power demands on all European ports. But the details are still being worked out, and we'll see what comes out after Parliament has voted. But for sure, there will be demands for onshore power on the container side. I think what's being discussed now is the cutoffs and the sizes of vessels that must connect to OPS. But so this is very much in our focus at the moment, and it will be interesting to see what the regulators come up with. But for sure, this is sort of as an onshore power, package. This is most probably the one that's going to be the next focus for us. Then finally, we have the Hernesaari Cruise Center. Again, you see situated very close to downtown, and the industrial area that is right next to the quays is also being converted into residential areas. So here again, we have the same reasons for doing OPS in addition to the carbon savings. Nikolai did a very good job, I think, in summarizing the challenges for building onshore power for the cruise vessels. It's many magnitudes more expensive than doing it for the liner traffic. You need the frequency conversion from 50 to 60 hertz. There's the huge power demand, which puts a lot of strain on the existing electricity grid. So we most likely need to build a 110 kilovolt substation, and then so on and so forth. So this does not come cheap. In addition, maybe our situation is even worse in a sense than for Copenhagen, that the season for cruise vessels up here in the north is very short. If we compare it to the liner traffic, where, as I said, you have the same vessel coming every day of the year, regardless of weather, with the cruise sector, it's not the same case. From when the first vessel arrives until the last vessel leaves in the autumn, it's about 6 months. But we can almost say that the very active cruise season is only 4 months of the year. So that makes the business case very difficult compared to the liner traffic for all these reasons that I just mentioned. Then, of course, in addition, the whole world has suffered from COVID now for a couple of years, and the cruise industry has suffered very badly from it. And now we have the war in Ukraine that is also has affected at least cruises in the Gulf of Finland and to Helsinki. There has been actually quite a significant number of cancellations for this summer that seem to be directly related to that war. So all in all, a very challenging situation from sort of almost every aspect you can look at it. But we're in a consortium together with the CMP, Nikolai, and Stockholm and Aarhus, and our ambition is, of course, to be able to bring as a consortium onshore power for cruise traffic to the Baltic, so that it's possible for a vessel to connect in almost every port on its rotation. I just wanted to show you the CO2 emissions since 2015. That is the year our carbon neutrality program takes as a starting point. And you can see that it looks very good. The light blue line is the linear line. And then you can see that now in 2021, we are well below it. And then you can see the different emission sources. I'm sorry, the caption is in Finnish, but the dark blue bars are vessel traffic. So the reason for us being so sort of far ahead of the target, I say there are three main reasons. First of all, we switched completely to carbon-free electricity, so that affected the green portion. Then there have been new technologies and new vessels that emit considerably less than the older ones. But then, of course, it needs to be mentioned that the decline in traffic during COVID, of course, that plays the largest portion at the moment in the dark blue sector with the vessel emissions. But regardless of COVID, we would still be much ahead. It's difficult to pinpoint exactly where we would be without, because there are so many moving variables. But definitely the direction is right, even though we think that the emissions are going to go up actually for this year because of increasing traffic again. This I thought was pretty interesting. CO2 emission sources relative. If we compare 2015, the starting year of the program, and now, you can see that the smallest piece of the cake that's our own direct emissions has dropped from 4% to only 2%, again because of the carbon-free electricity. But the vessel portion of emission has also dropped actually quite significantly. And that, since we're looking at the relative, it means that the heavy traffic and heavy equipment, their relative portion of total emissions have gone up. But this does not mean that they have gone up in absolute terms. But I thought this was a very interesting sort of finding that, of course, makes perfect sense when you know what has been done and what has happened. Finally, just a few words on next steps and lessons learned. I mentioned Fit for 55, and that's most definitely going to be very interesting and something that's going to affect not just us but every port in Europe. So it's going to be very interesting to see what we get out of that. Not only regarding the OPS requirements for the ports, of course, that affects the ports directly, but also in the inclusion of the maritime sector into the emission trading scheme, taxation changes on fossil fuels or traditional bunkers, but also on onshore power sales. So everything is going to add up to the picture, and so it's going to be an interesting couple of, let's say, 8 years now that we still have left until the year 2030, when the Fit for 55 package should be implemented according to the Commission proposal. So that's for sure something that everyone is going to be focusing very much on in the coming years. We have a very big, for our size at least, a development program that is about to start in the downtown harbors, where we're rearranging traffic to free up some areas for other uses and to become more effective. So, but that's going to include building of new quays, most probably building of new passenger terminals, building of a tunnel for the heavy traffic from the West Harbor and directly to the highway. So these are also actions that it's very much going to affect us for almost the coming decade, I think. So we're now right in the middle of the process of updating our strategy accordingly. But for sure, these issues that I've been talking about and we've all been talking about today are going nowhere. On the contrary, they're just becoming more and more important all the time. So it's going to be a very interesting couple of years, I think, for all of us. I'll stop here since I was a little bit late to start. So thank you very much for your attention. And please, feel free to ask questions or connect, and we will take the discussion further. Thank you.
Yes, Andreas, thank you for the presentation. I'm really pleased that we managed to have your presentation and for you to do it. As yourself in Port of Helsinki is a great example of what we've seen achieved, accomplished, and plans of the port in the future, the green port, what Port of Helsinki represent. We've heard your issues and challenges and what you are facing right now and probably in a short term as well. We've seen that you're collaborating as always with the regional ports on EU level. And as you mentioned, the opportunities for deployment of OPS for eventually for cruises and for container vessels there maybe a question. What do you think is the path for the midterm and the deployment of this infrastructure? Are you planning to go ahead again with this multi-project type of initiatives, or you going to continue on your own according to your geopolitical regional issues, what are now appearing again?
Yeah, it's a good question. On the container side, I think everyone is first of all waiting for Fit for 55. As I said, but I think then after that, after we know the regulatory demands, the next step is going to be to have a discussion with the shipping companies to see in what timetable are they actually going to implement what's needed from them to be able to connect to OPS in the port. Because it doesn't make sense to just run ahead and build a lot of OPS for container if no one is able to use it. And plus, of course, you must have the discussion with the shipping company to realize that what are the technical specifications and demands and so on. Of course, there are standards in place that are fine and well, but for example, the positioning of the actual equipment and where will the connection points on the vessel be, and so on. So you're most probably going to need some type of mobile solution also for a container in the same way that you most probably need for cruise vessels. And mobility it's always difficult in a land that has a lot of snow and ice in the winter. So there are a lot of technical challenges for sure to be solved. But the power demand, at least from the size of container vessels that we receive, is not going to be, still it's a huge amount of energy, but compared to cruise or something like that, it's a lot smaller. So from that point of view, it won't be technically as challenging as doing it for the cruise sector. But as I said, there are other aspects as well that are still unsolved because we yet don't know what we're actually have to work with.
Yes, thank you, Andreas, for your comments. Appreciate your presentation and presenting what is the latest happening in the future plans for Port of Helsinki. Thank you.
Thank you. Thanks for having me.
I would like to move now to a short comment and a summary of our event. I would like to say that we had excellent presentations by our speakers and interactions with the participants. We started with the different charging solutions for ships in port, ships battery design and charging systems, as well as various ships available. Also, we've seen the OPS technology solutions and the current deployment and future plans in the ports, as well as EU co-financing opportunities. A few words from my point of view. In my opinion, electrification, different charging solutions and OPS infrastructure, as well as constant ships battery optimization for ships, represent important solutions to limit the pollution and emissions caused by ship engines. It remains to be seen on what term this is going to be speed up. This challenge could prove an opportunity. I also like to say that the Baltic Sea region is clearly, as always, leading area where the OPS infrastructure is continuously progressing, supported among others by the efforts of Baltic Ports Organization on numerous initiatives. And overall, according to the increasing trends of OPS in the Baltic ports and electrification of ships on EU level, it can be said that the good future for shore-powered and charged ships is exactly what we can expect in the coming years. However, what remains to be seen is how the vessels will use this infrastructure. Will demand grow up, and to what level? Of course, it's important to underline that close cooperation is needed between ship owners and ports. And by doing this, it will be that full benefit from existing OPS installations and charging facilities. So, dear colleagues, I will have to mention that we had today attendees from all across Europe. All presentations and the entire video recordings will be shared with the participants and, of course, with the presenters. Also, will be available on our YouTube page and of course on a web page for sharing. So once again, thank you to all the event partners, presenters. Thank you for participants for joining us today and hope to see you soon. Thank you all and see you soon.